Welcome to Decoding Healthcare Research. I'm your host, Efrain Riveros, Dr. E.F. Brain. Today, we are going to continue talking about body weight. And in this occasion, we invited an expert, Dr. Nori Geary. He is a researcher. Actually, he retired, but he did a lot of research for the Department of Psychiatry, Weill Medical College of Cornell University in New York in the United States. We are going to be discussing control theory models in the context of body weight. And I want to start by welcoming you, Dr. Geary, and thank you for being with us today.
You're welcome. It's a pleasure to be here.
Thank you. So body weight has been central lately, and there is a lot of concern because it became an epidemic in the world, not only in the United States. And there have been different ways to approach it, and one of them has to do with the relationship between the body weight and the regulation of that body weight in terms of appetite. So my first question to you is, what brought you to approach body weight from this perspective?
Oh, that's a good question. When I was in graduate school back in the dark ages, my advisor was interested in using control theory to describe some behavioral regulation of body temperature. And I had quite a bit of math as an undergraduate, so I took to this theory, which is a mathematical theory, and have had it in my head for a long time. I had a friend in the field who wrote several papers that it was quite a very active controversy whether a control theory or how a control theory could be linked to body weight in the 80s. And that seems to have died away, as these things do. More recently, a guy at NIH named Kevin Hall started applying control theory or started mathematical modeling of different aspects of body weight. First without control theory and then with control theory. So I followed his work quite a bit and tried to popularize it in some of my writings. Yeah, so that's kind of where we are. It's a little bit my retirement hobby.
I see, and it has a lot of interesting points. Most of them even difficult to understand for a lay person like myself. So I'm going to ask you some questions that may seem simple, but I am sure our audience is going to enjoy the way you present it to us. So the first thing I want to know is in terms of let's go back actually to what is control theory to start with.
Yeah, control theory is the mathematical modeling of feedback relationships. And I'm sure everybody in the audience is familiar with many, many feedbacks in physiology that operate to regulate some kind of variable, a hormone level or something like that. This can be modeled mathematically. One of the reasons not many people do it is that the mathematics is a little bit forbidding. It's a little bit beyond the first year of calculus you had. These days it's done computationally rather than with trying to derive a mathematical equation. But the theory is quite powerful in terms of, it's ubiquitous in engineering. So anybody who's an engineer has studied control theory. And in physiology, there are many areas. In glucose regulation, for example, aspects of glucose regulation have been modeled mathematically. Probably many of the audience is familiar with insulin resistance and glucose levels related to insulin resistance. And there are many mathematical models of that, which they may be familiar with.
Correct. So, and I think it's clear, and that's a good starting point. How does appetite as a behavior fit into this control theory?
So if a variable is regulated, let's say body weight, if body weight is regulated by negative feedback, that essentially means that some aspect of body weight is sensed, and that sensed aspect controls some behavior or physiological response that influences body weight. So in the context of food intake, which is probably the major thing that causes changes in body weights in adult humans, food intake, a feedback from body weight is sensed by the central nervous system, produces a change in appetite. A lasting change in appetite, of course, will have an influence on body weight. So that's the crucial thing. There's a circle. The regulated variable has an effect, has a feedback, which has an effect, which influences the regulated variable. So if you have that so-called closed circle or closed loop, you're dealing with a feedback relationship. Yeah, so people have computed, and I can show a little later, some models of how appetite probably is changing in various contexts of body weight change.
Yeah, that interrelationship between body weight and appetite is dynamic from what I understand. And you use, or you mentioned two different models. One is the set point, and the other one you name settling point. That is like a simple negative feedback. Can you illustrate a little bit about the difference between the two models?
Sure. This nomenclature goes back to the late 70s in that debate I referred to earlier. And the people who were on advanced one type of model named their model the settling point model. And that's actually entered into physiology a bit, but it's widely misunderstood. So let me start with the more complicated model, which is the set point model. It's easy to explain, well, I don't know, maybe not in Georgia, but in many parts of the world, homes have central heating, or maybe your home has central air conditioning. And that usually means that there's that the temperature of the rooms inside is regulated. The temperature is actually the feedback signal. That's no problem with that. So the temperature is the regulated variable. The feedback signal is the temperature, and that turns a furnace on or off, or an air conditioner on or off. And almost all houses in the last century that have a central system have a thermostat, which means you can set the desired temperature. And that's the set point. It's a control system that has a desired level that can be externally set. It's actually not used as much in engineering. Well, it's used a lot in engineering. I won't say that. The question is it applicable to body weight? Is there a set point for body weight? Now, the alternative is there is no set point, and the control mechanism has negative feedback that might control appetite, and that influences, that combines with other variables. So maybe the control system says you should eat less, but the obesogenic environment, as we call it, of all these palatable, mostly high-calorie foods, is driving you to eat more. So you have two antagonistic influences. And if one of those influences is part of a negative feedback loop, you'll reach an equilibrium if the influences are constant. And that equilibrium is what this guy named Jack Davis referred to, and his colleague Virchow referred to as the settling point. In most of physiology, people say there's a set point for this, for body temperature, for the other thing, but they never found one. And people think that because you have a set point, the system should be precise. That is, the temperature should actually come to that point. But that's not really true. The key to the performance of a system is how the feedback is processed to influence the regulated variable. So how the appetite is processed. If the feedback effect, it's technically called the feedback gain. So maybe on your amplifier, you have a gain signal. The feedback signal is processed and the result is the feedback gain. If the feedback gain is strong, then you'll have pretty good regulation. You'll get close to the initial level of that regulated variable. If it's weak, you won't. Whether or not you have a set point. Yeah, to get ahead of myself a little bit, but maybe we can come back to it later.
So, but
yeah,
yeah,
go ahead.
And it's this is a super important concept because we tend to think in simplistic terms that there is a point that is kind of fixed, and the body has to go back to that point no matter what. And what you are saying with the settling model is that there are multiple variables playing, and the set point is kind of more dynamic, if you will, right? It's not something fixed, but the body senses depending on different probably.
The settling point is dynamic. It's fixed. It's set. It's the result of the circumstances. So if you have a chronic or tonic influence of one sort added to a system, it'll change the equilibrium. So it's like an equilibrium. What I often say is that the regulation opposes change, but it doesn't have a set goal that it's trying to get back to. So there's a little bit subtle difference there. You can oppose a change without that set goal. And the equilibrium point is not that you observe, the body weight you observe, even if it's constant for a long time, is probably not a set point. It's an equilibrium, which could change if your environment or somehow an external influence affects you.
Yeah, and that's actually good news, right? Because if you are able to affect those variables, chances are that that you move along that spectrum of dynamic movement of the variable, and you have the ability to somehow change things by affecting the environment, I guess, right?
Yes, I think so. You can imagine as well, since we believe that this whole feedback system is realized in the brain, you can imagine that it might be possible to affect the neural network that produces the feedback gain, for example. And there's some fairly recent research that suggests that we might be identifying some of the neural populations, the small sets of neurons in the hypothalamus that may actually be, in some circumstances, the critical neurons determining feedback gain and therefore determining the body weight. But the environment's also a big thing. If we get rid of high fructose corn syrup, for example, who knows? Some people think that's what caused the obesity epidemic.
Yeah, you are completely right, and we have been digging deeper into that. And now that you mentioned the environment, so what physiological signals are actually variables that can be included in the model? So what, besides just the weight, the soul weight, what variables are really affecting the model?
Well, about 25 years ago, a hormone was discovered called leptin, and everyone who reads about body weight reads about leptin. And it was discovered that leptin levels are correlated with fat mass. Of course, insulin levels, basal insulin is also tightly correlated with fat mass, as was discovered 50 years ago by Dan Port. So those are two hormones whose basal levels could be feedback signals for fat mass. Now, in trying to work that out, it's turned out to be, of course, quite complicated. At this point, the research with leptin, which has, of course, got the most publicity and the most work because it linked right into the revolution in molecular biology 25 years ago. The research with leptin seems to indicate that it probably is a feedback signal for underweight, but not for overweight. And this is shown by the fact that leptin levels are increased in overweight, and yet the relationship to body weight or to fat has changed. And when they tried to use leptin as a therapeutic tool, injection of leptin or long-acting leptin analogs didn't really have much effect on obese individuals. But replacement of leptin had major effects on appetite and in women on fertility, actually, in people who are very underweight. So leptin might be a feedback signal, but unfortunately not effective in the obese range, only effective in the underweight range.
Yeah, exactly, because it depends on the fat mass as well, right? So we have been talking about appetite and body weight regulation, but there is another variable that is intervening all the time, and is energy expenditure. And it's been said that one of the difficulties for people to lose weight and actually to regain that weight is some adaptation to energy expenditure. Is this a variable that should be included in these models?
Yeah. If it depends to a certain extent on whether you're a man or a mouse. A huge amount of research is done in mice, and in situations where they change body weight, it seems like energy expenditure is the key, most important variable. A slightly larger animal is actually several-fold larger than a mouse, is a rat, and there both food intake and energy expenditure play an important role. And then when you get to humans, it's clear that there are effects on energy expenditure, but over the long term, it seems that food intake is probably the predominant effect. There's a very classic experiment. Let's see. So this is a slide that describes the key results in an amazingly wonderful study done by Rudy Leibel and Jules Hirsch at Rockefeller University almost 30 years ago. They got us, they had a number of volunteers who either were of healthy weight or had long-term obesity, living on the metabolic ward for quite some time. And you see on the left panel the healthy weight and the right panel the obese. They started at their usual weight, either healthy or obese, and overfed them or underfed them. So they gained or lost 10% of their body weight. So the symbols to the left and right of the vertical dotted lines are at minus or plus 10% body weight, which is on the x-axis. And what you see on the y-axis is their non-resting energy expenditure. That is the energy expenditure that was not related to their basic metabolic rate, which is largely set by lean body mass. It's the energy expenditure in daily exercise. Of course, in the metabolic lab, they didn't do a lot of housekeeping or things like that. But moving around, fidgeting if they fidget, which can be quite a few hundred calories a day in some people, things like that. So non-resting energy expenditure. And what you see is that the two sets of data are almost perfectly parallel, that both obese and healthy weight people, or people both with obesity and healthy weight, increase energy expenditure, non-resting energy expenditure, if their weight goes up. So that tends to drive the weight back down. And they decrease it if weight goes down, which tends to drive the weight back up. So this is probably one of the first very convincing demonstrations that energy expenditure, the adaptation of energy expenditure, plays a role in human body weight regulation. Now, the last thing about this slide is that the effect is, it's hard to know how big it is. They measured it and they didn't keep going for weeks, which you might have to do to get a really good answer. But you can see it's kilocalories per day per kilogram of fat-free mass. So how many kilograms of fat-free mass do you have? 50. So it's maybe 10 times 50, 500 kilograms in healthy weight, 500 calories a day. That's quite a bit and would certainly affect body weight. So this is a very important study that was published in the New England Journal about 1995.
Yeah, and it's very clear the role that the energy expenditure is playing here, and
yes.
And I want to move on to the mathematical part of the models, because it's fascinating. Sometimes not that easy to to understand, but I am sure you can digest it a little bit for us. So can we talk about the models themselves?
Yeah, sure. If you scroll down, I'll tell you when to stop. It's not much further, I think.
Let me see what how I can go back to.
Next one, probably.
Yeah, maybe this one.
Yeah. So we start here. Yeah. So if you're an engineer and you're designing a system, you start with a so-called system diagram. And that gets all the variables on a piece of paper with a bunch of arrows linking them. So this slide is a basic system diagram for a negative feedback control of body weight with no set point. Because as I said, the set point is probably not too important in human body weight control. So you start at the top with a regulated variable, and then you have a feedback signal. And then the feedback signal is transformed into a feedback gain, which I think is regulated weight regulatory appetite and adaptive energy expenditure. And that goes into some sort of summator with the Greek sigma symbol. And it summates with all the other controls that are not part of this closed loop. So conceptually, we can divide those into all the normal controls of food intake, and then maybe the additional influences caused by the obesogenic environment, so the pathophysiological controls, if you will. And that summation ends up with controlling the total energy intake or food intake and energy expenditure. And that, in turn, controls body weight. So you have the closed loop and some disturbances on the outside. Now, in order to actually make such a system, you have to have machines at each step that do all this stuff or model physiological things. The simplest models are all, well, first of all, everything is represented as a mathematical equation. The feedback process is a function of body weight. The feedback gain is a function of the feedback. The summation is a function of the feedback plus the other controls. So it's a bunch of equations. And the simplest situation is to make them linear equations. They could be anything, but to make them linear produces a very powerful model, which we'll see actually describes a lot of human body weight dynamics quite nicely. So we go to the next slide. Which I forget what's on it. Yeah, so so the assumption is that all the equations are linear, and that means the feedback gain is linear. So a stronger feedback gain is shown in the dotted line, which is a steep slope. So you get stronger feedback, the effective feedback is stronger with a small change, and the weaker feedback gain is shown in the solid line. So not so much effect of the feedback. Now, next one. So if everything is linear, as I said, you have an equation for every step in that first circle. It's already a little bit complicated. So one thing which is usually done is you can forget about the total body weight and just model the change. So you can set all the initial variables to 0 and just look at what changes. And now you have a linear equation for the change in each thing. So in the middle of the slide, I said, for example, the linear feedback from body weight would be F feedback equals K, the constant of slope or proportionality, body weight. And all the equations are like that. And that is actually, if you now want to understand what's going on over time, you have a differential equation. And that's where people get lost right away because they don't really understand differential equations very well, which is perfectly understandable because it takes a lot of time to get there. You have other things to do if you're doing physiology. So a differential equation is the change in feedback over time is equal to K times F. So it's a very simple differential equation. Excuse me. Now, if we go to the next slide, which is the last math.
Okay. So let me use.
So as I said, we're setting everything to 0 and just modeling changes. And we're setting all of these constants we're setting all the equations to be linear. And if you now combine all the equations that are in a chain into one equation, you can get all the variables that are in the model into one equation. So now the change in body weight over time equals this unfortunate looking nasty equation here, IK times E to some exponent.
Yeah.
So I is the constant describing the obesogenic environment. It's the constant driving food intake, the disturbance that increases food intake. K sub F is the feedback constant, the constant of proportionality of the feedback signal. E is Euler's number. And the exponent, we don't have to worry about too much, because I just want you notice it's a negative exponent. So as that exponent gets bigger and bigger over time, E approaches 1. So I can't see the bottom part of the slide here. But I think what I have down is written, I solved the equation for body weight at time t. And it says, can I move this? Something, no, I can't. Yeah, okay. So the body weight at time t, get rid of the differential equation, and solve for body weight at time t is equal to I divided by Kf. So the disturbance divided by the feedback gain times 1 minus E to this exponent. And E to that exponent, as I said, if you imagine what happens to that over time, well, it's a negative exponent. So as it gets larger and larger, it approaches 0. So that phrase, 1 minus E to the something, approaches 1. So body weight at time t, the steady state after a long time, is simply I divided by Kf. And now the last equation is integrating body weight at time t to get an expression for the change in body weight. Oh, I guess it's the next slide. Yeah, go to the next slide.
Okay.
Yeah. So as time goes by, what's the body weight after a long time with these two variables tossed in? And the equation says O to the T, but that, I'm very sorry, that should be body weight. The O should be body weight. So body weight at time T equals this expression, which becomes I divided by Kf when the right side of the expression goes away, when it becomes close to 1. So what linear control theory predicts is that the strength of the disturbance divided by the strength of the feedback gain gives you the new body weight, the new equilibrium body weight. So that's pretty powerful if it's somehow mirrors reality.
Yeah, correct. Especially in terms of the disturbance, right? The magnitude of the disturbance has a huge effect.
Yes.
On the system.
Right. So if you imagine, well, let's see, I think the next slide shows it. Next slide, please. Yeah. So if you look at the top, it's showing you exactly what you just asked about. What happens when the strength of the disturbance, the I, the obesogenic environment, is increased? So in the top graph, if you start at the left, it's 1 to begin with, then you double it. And you have an exponential rise to a new constant steady state, which is essentially twice. The change in body weight is twice. And then if you take it away, it goes back to where it used to be. And if you cut it in half, it decreases a lot. So that's what happens. There's basically a linear change that takes an exponential function to get there, but it's a linear change. And then the bottom part of the figure shows exactly the same thing, except we're leaving the disturbance the same and changing the feedback gain. And that sort of implies that a key to the performance of the system is the strength of the feedback gain.
Yeah, that's amazing. That's amazing how you can illustrate it in that graph. That's great, and I think it's a good way to understand it. So in terms of strengths and limitations of the model for potential like clinical implications. So what do you think is the main strength that this model could add to the understanding of the relationship between body weight, appetite, and energy expenditure?
I'll say two things. First thing, it's although there's a little math in it, it's a simple model that doesn't have a set point, and the notion of the set point has confused so many people for so long that it's not necessary from the control theory, and it doesn't help. So I think getting rid of the set point is one thing, and the second thing I'll say is that it fits a lot of data, and I can show you a couple of examples if you want to go back to the slides. Yes. Of some very nice fits. So yeah, that's good. Let's go back to the previous slide. This was a very nice paper published by some leaders in the field 10 years ago, no, 8 years ago, 7 years ago. So the data were generated by a guy named Randy Seeley, who's a leading basic researcher in rat obesity, but he collaborated with some endocrinologists at his institute when he learned about the operation of some sodium-potassium inhibitors that cause massive increases in urinary glucose outflow. And then, to his credit, he approached Kevin Hall, who was the guy who does a lot of these feedback control models at the NIH, and they generated with this data, these amazing data. So if you go to the next slide, so this sodium glucose link transporter 2 antagonist increased urinary glucose by about 360 kilocalories a day. So these were people with moderate obesity. Some were less, some were simply overweight. They had type 2 diabetes, which is the reason they're getting this drug. And they basically put them on the drug, and the patients did well on the drug, and they recorded their body weight every month or so for a year. So here you see the body weight, and those the body weight of the squares, and the line is the model for a simple negative feedback control. Starting at a 0 is again modeled to the change. So body weight change is 0 at week 0. That is to say, there's no change, and body weight goes down. But after a year of losing 360 kilocalories a day, they only lost 4 kilograms. If you transform 360 kilocalories a day into the total loss over the year, it's 130,000 kilocalories, which if you use this overly simplistic 3,500 calories per pound of fat, that's 38 pounds. I said kilograms. I think that's pounds. So it's 20 kilograms. Sorry about that. So instead of losing a spectacularly large amount of weight, they didn't. And instead of having a linear decrease in body weight, they had a negatively accelerated decrease in body weight that was predicted with amazing accuracy by this simple model. Now, if you go to the next slide, they computed, they did one other thing. They put in an integral control, which is usually the advantage. If you have a set point, you can actually accumulate the error over time, not just work with the error at the time, which is what we've been talking about so far, but to accumulate error over the last month or whatever. And they made some assumptions about what the best set point model might be, and then fed the data into that. And you can see by the dotted line that it didn't fit at all. So if integral control is the usual advantage of a set point, it didn't seem to work here. And then the next slide shows the model of food intake. And again, the points here are not data points. They're modeled food intake based on modeled energy expenditure and the observed body weights. And you see that it looks like they labeled it food intake, but I think in honesty, it's really the sum of adaptive thermogenesis plus food intake. But you can see that by either or both food intake and adaptive thermogenesis, they decreased caloric expenditure, excuse me, by about 350 calories a day. So they basically got to a point where they were changing their energy balance at net zero because they'd adapted perfectly to the urinary glucose.
In opposite directions, right?
Yes, in opposite directions. So that seems like a very strong control against loss of body weight in this situation, which can be very nicely modeled. And now if you manipulate the system in different ways, you can predict what the changes should be, kind of waiting for experiments like that to be done.
That is amazing, right?
And these, of course, are not patients who are being treated for weight. I want to emphasize that. They're told to eat a healthier diet, but they're not in a weight control program. They're just in a diabetes control program. So they don't know they're pissing away 350 calories a day. Yeah.
Wow, this is very, very interesting and applicable, right?
Yes.
At the same time.
So that is described in detail in the paper we're talking about. But I want to show you some data that didn't exist when I did that paper. So everybody in weight control knows that the pharmacological tools available are getting very powerful. And so far, the key is that the new tools are stable agonists of GLP-1 and usually some other hormone. So the initial GLP-1 stable agonist, liraglutide, produced about 10 or 12 kilograms weight loss, which is the best thing other than bariatric surgery. This one, which I guess is Mounjaro, but tirzepatide, this is the initial big paper showing its effect in a weight loss trial. And you can see you get 20 or 22 kilograms over the course of, again, I'm blocking the bottom here, course of about a year, I think, year and a half.
Yeah, a year and a half.
So if you look at this curve, at the bottom curve, the highest dose, it looks like an exponential decay. And so I fit an exponential function to that, and the exponential function fit with a 0.86, which is to say that 86% of the change was accounted for by the exponential model, which fits nicely with other data from previous types of drugs that have been fit. So what that is telling you is that the math is consistent with a negative feedback control theory, a linear negative feedback control theory, operating in this situation. That is to say that the interpretation is not that the drug, that the patients become tolerant to the drug. The interpretation is the drug is equally effective the whole time, but there's an active negative feedback opposing the effect of the drug, which slows down the rate of weight loss and leads finally to an equilibrium. Now, it's a very good equilibrium. It's a lot of weight loss, but it's a lot less than if the initial rate of weight loss were maintained. So it's an active feedback system, I believe, that is causing this deceleration of weight loss. And again, opens up targets.
Right, and we may argue that, and for our audience, these medications belong to the same group of Ozempic. One of the implications, at least in theory, is that because all these mechanisms are opposing the effect of the medication as predicted, as the model is showing, when you stop the medication, most of these adaptive mechanisms are going to kick in, and that may in part explain the weight regain after the patient stops the medication, right?
Exactly. If what the theory predicts is, excuse me, if you stop the medication, if you stop the disturbance, then the theory will bring you back pretty much to the baseline. And I didn't bring a slide. That hasn't been done. It has been done with this drug, but the trial has only been about, I think, 20 weeks published. But body weight goes right up, and it's still increasing at the end of 20 weeks. And every other drug, and the slightly weaker drugs that have been tested previously, body weight goes back more or less to where it started if you end the medication. Yeah, so wouldn't it be wonderful if we could understand how this feedback control worked, and if it was a certain set of neurons in the brain that we could either have a very benign drug that affected them, maybe this drug does something like that, or maybe we could imagine a transgenic mutation that that would knock out just this very small population of neurons, if that's the case, that it is a small population, and you'd have a permanent fix for obesity without having to take a drug for the rest of your life.
Yeah, that's absolutely true, and it's fascinating to imagine all the implications that that may branch out from the fact that we are able to apply these models and to predict somehow what's going to happen in the future if you affect or tweak certain variables. And this is actually leading me to my next question, and is in the future, what do you think is the role of this type of models into a clinical practice in terms of aiding the practitioner make decisions?
That's a good question. Of course, I'm not a clinician, so my answer is going to be naive, and I haven't thought too much about that exactly. But I can imagine that, yeah, if you read the obesity research literature, there's a journal called Appetite, which studies appetite, obviously, and there's a tremendous variety of dysregulated, the people like to say, types of disordered types of appetite, not to the extent of a psychiatric disorder like binge eating disorder, but psychologically strong effects that seem to be very regular. And the question is, could some of those effects influence or mimic the drug actions? Because it would be nice to get rid of drugs. So if we could select groups of patients who vary in the terms of certain types of eating disorders disordered eating that they display, be put in some sort of factorial design with some of these anti-obesity drugs to see at what point in the course of the therapy they might be relevant, or can they replace the drug to some extent at some point of the therapy. Getting rid of the weight is probably the hardest thing, so perhaps maintenance might be an option for something that could be similarly efficacious but not require drugs. And maybe, since you asked almost at the beginning about energy expenditure, I should reference some classic work of a woman at Brown called Rena Wing, and obesity researcher called, well, she is one as well, another obesity researcher called James Hill. And they were looking at just lifestyle modifications as they existed in the 90s. They've been improved, and looked at the range of body weight outcomes. And the range was spectacularly large. And they did all sorts of psychological tests and life history records to determine what differentiated the more successful and the less successful patients. And the only thing they found that was relatively strong was people who engaged in regular exercise had the highest likelihood of maintaining weight loss after initial diets, when they were sort of, say, turned loose. And that has held up. So yeah, there's an example of something which by itself has only a minor effect on body weight, but might, under certain circumstances, be something quite useful. And maybe exercise plus a much lower dose of drug would be a maintenance option.
Yeah, exactly. So the incorporation of different positive aspects into the environment and being able to model or making them part of the model is definitely something that is, probably has a bright future in store in terms of research and clinical application. And I think, and I want to close this podcast by saying thank you so much. The way you present this paper is wonderful, and it's definitely adding value to the research that is being done in body weight. And the way you explained it to us was very clear. Thank you so much, Dr. Geary.
You're very welcome. And I have to say that you asked excellent questions. So I've talked to many people, and very rarely have I had my opinion that I've maybe communicated somewhat effectively. And that's in large part because of how you led me through the conversation. So thank you very much.
Thank you so much. And for our audience, I'm gonna put the link to the paper in the description of the video, and see you in the next episode.